All right, so welcome to Math313. This is lecture 13, so we're continuing our work on monovariants. And there's another word that you can use for monovariants for a large class of problems, which we'll see today. So what I want to do is I want to do some tiling problems. You might remember we actually did a tiling problem towards the start of the semester when we had a 2x n board and we were trying to cover it with 1x2 tiles. And we got the Fibonacci numbers, and this is what led into our study of recurrence relations. So what we're going to do today is we're going to look at a different kind of tiling problem. We're going to have a checkerboard or a chessboard, but we'll make it n by n. And we'll have a set of 1x2 tiles. And the goal is to put the tiles down in such a way that the entire chessboard is covered. But there's going to be a twist. We remove the bottom left and top right corners of the board. So, can this be done? Okay, so here's our problem. What do you think will be useful to solve this? I have to ask the question. Probably monovariants, as this is the monovariant unit. What should we do, though, before we jump to monovariants? Small cases. All right, so let's do n equals 1. All right, so if I remove the bottom left and the upper right, this is not that challenging. There's no board. So this is an interesting question. Does it work? Can you tile it? If your definition of tile is to cover every square, then yes, it works. It's tileable. All right, let's do n equals 2. So now, what do you think? So it does not work. All right, so we have 2 data points, so maybe all the odds can be tiled and all the evens cannot. Well, okay, let's try n equals 3. I'm on lots of medication, so maybe that's why I'm saying things like this.
The odds are going to happen on number of squares, right?
Okay, good. So I'm not even going to bother doing this because you made the observation. More generally, if n equals 2m plus 1, we have an odd number of squares. We would have 2m plus 1 squared minus 2, which will be congruent to 1 mod 2. It's an odd number of squares. Every time we put a tile down, we remove an even number of squares. So if we have t tiles cover 2t squares. So we can't do any of the odds. All right, so this makes things a little bit easier. So we only have to understand the evens. Now we could probably do this with a monovariant. And the monovariant would be the number of squares uncovered. And that would always be even. Oh, I'm sorry, that would always be odd, because every time we put down a new tile, it stays odd. So if you want to use highfalutin language and really just overkill what's going on, your monovariant would be the number of untiled squares. It's always going to be an odd number, so at the end of the day, there's 1 left. This is similar to the triangle game we played with Kayla, where the number of such triangles turns out always to be odd. This is a great way to deal with a lot of problems. Odd numbers can never be 0. Okay, so let's look at n equals 4. So this is probably the first non-trivial case. So we'll have 1, 2, 3, 1, 2, 3. And now we remove. Do we have an even number of squares? Okay, so if it's not doable, we're not going to be able to at least get it through a trivial reason. We're going to have to do some work. Without loss of generality, how is the first tile placed? How many ways are there to place the first tile?
Can you place it in the top left corner, and either way, it's the same by symmetry?
So we could place it, it could be either there or there by symmetry. Something has to cover this one, right? So we could start doing the analysis. We know we have to have this. So let's see if we can actually just do this by brute force. We know we have to get this square. How many of you have ever played the game Free Flow or Bridges? So in that game, you have to make sure you go through every square. You can use this to really simplify the analysis. We know we have to get this. The only way we can get this is to come down like this now. Well, we know we have to get this. So we have to come down like this. Well, we know we have to get this. Now, there may be other ways to do the analysis, because instead of looking at this one, maybe I could look at what comes next over here. Well, actually, that's not good over there. It's not good. So this was probably the best way to be going. And now what happens? We have to now come up like this. Or I could come over like that. So depending on which choice I make here, I'm going to get a different contradiction. That's fine. So let's say I like leaving something in the interior. It just seems more fun. So there's no way to get this square. So in the 4x4 case, there's no solution. We could try to do this for larger and larger even boards, but my feeling is it's going to get harder and harder and harder to make this analysis work. So do you think it's possible to cover even boards? Maybe it becomes possible as you go higher up. Maybe 4 is special and small. All right, so we probably want a monovariant. Any thoughts on what the monovariant is? Yes?
So I think maybe if we color our chessboard according to the chessboard.
Ah, good. So actually use the fact that I said that this is a chessboard. A chessboard has a natural coloring on it. As an interesting challenge, my kids and I just tried to see what is the maximum number of queens you can have on a chessboard in a legal game. This would involve people playing very foolishly. Anybody want to guess how many queens you can legally have?
18? Can you have 18?
So can you do, is there a number that would be higher than 18? No, because that would be if every pawn scores and the 2 queens aren't checked, aren't killed.
Both of the queens could be like around the king.
Yep, yep. So as an interesting challenge, it is possible to have 18 queens. It is also possible to have 20 bishops. This requires some of the most foolish chess moves possible. But if you want an interesting challenge, come up with a legal game where you have all the pawns scoring. And you've got to be careful because pawns are facing each other, so how do you get them around? But use the fact that it's a chessboard. So if it's a chessboard, I'll just draw a subset of it. We know we have some kind of coloring pattern. We have black and white squares, and so using white chalk on a black board is actually pretty good right now. So we have something like this. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, so here is my chessboard. And now I remove 2 squares. I remove the bottom left, and I remove the top right. Okay, what should we choose for the monovariant?
Well, you've just removed 2 black squares.
We remove 2 black squares. So there are many choices of monovariants you can do.
Why can't we just say the obvious, like?
We can. I'm trying to say it in such a way that I get to use the concept of monovariant. You could also use,
You know,
I mean, you could also use like the shorter word parity
the uncolored squares minus the colored squares.
on the board.
Yeah.
Yes, so what we could do is we could look at number of white squares minus number of black squares uncolored, or untiled.
Are we saying that black is shaded or black is the unshaded?
Black is the unshaded. This is clearly white.
Well, then you wrote black.
Oh, sorry.
So, like,
No, we removed two white squares. Sorry. Thank you. Yes, we removed two white squares. And so we can look at the number of white. Well, then if we're going to do that, we should probably do number of black minus number of white, because then we can have a positive number. And what does this always equal?
this would be an invariant.
So this is actually an invariant. It always equals 2. Because whenever we put down a tile, if the tile is horizontal or vertical, we get one of each. Each tile is either white-black, or white-black, or black-white, or black-white, in terms of what it's covering. So it leaves this unchanged. So as we just keep putting down more and more tiles, the number of black squares minus the number of white squares that are untiled is always 2. So at the end of the day, we can't have it covered. So there's a really nice simple proof to this. The mono-invariant or the invariant seems like a little bit of an overkill for language for this problem. And then you could start asking other kinds of generalizations. What kind of generalizations might you ask? Because again, whenever I give you a problem or whenever you see a problem in the world, if you can solve it, great. And then say, well, what else can we do?
You can change which squares you eliminate.
Yeah. So we could change the squares we remove. Right? So one possibility is, what if I remove 2 random squares? What's the probability the board is colorable? If I remove 2 adjacent squares, is the board always colorable? You know, a lot of good questions you could ask along those lines. What else could you ask?
You can change the shape.
Yeah, change shape of tiles. Right? Maybe now instead of using 1 by 2 tiles, maybe we have a collection of different types of tiles. There's another question. There's another natural generalization we could do. Yeah, we could change the board. We could even make the board 3-dimensional. Right? Lots of great ways to go about this. And then the question is, you know, how simple will the analysis be in these cases? Will you be able to make a very similar argument and say, well, look, if we're removing 2 things like this with all the stuff we're putting on, we're still going to be fine? My feeling is for some of these 3D boards, you know, if we keep it as a cube and we remove 2 things out of the same, the argument should follow very similarly. So these are lots of you know, tweaks to the problem.
But for a cube, I don't think, at least the that diagonal wouldn't change. Because if you take the white square and kind of extend a little line, the top, if the bottom's white, the top is black.
Okay, so then if that's the case, then this simple argument would not work.
And I think, I don't know, if you do it in 1 dimension, that's the same case. So it might be possible that for even dimensions it doesn't work on like far corners, and on odd dimensions it does.
Right. So I think in odd dimensions the argument would work very quickly. But of course in odd dimensions we have how many tiles?
If you have an even edge, you still have, right?
Well, so if we have a 2 by 2 by 2 cube, then the opposite corners are the same color? Or they're different colors now, right? So then the argument would not work. But if we had a 3 by 3 by 3, would they be the same color again? They'd be the same color again.
Then it would still be odd.
It would still be odd, exactly. And we don't really need to do anything clever there.
Yeah.
So the question is, if we took a cube, would we be able to solve the cube? If so, the simple argument like this is no longer going to work. And we would need something more clever. Okay, let's do another one where it's not going to be clear what the monovariant is. Okay, so the way this problem works, and you got to be a little bit careful on the phrasing, is you have n people and r rooms. And if you want, assume there's at least one person and assume there's at least one room, otherwise the problem is boring. So n people, r rooms. And then we're going to have a sequence of moves. Time equals 1, 2, 3, 4. So, discrete moments of time. And each one of these moments of time, we look around and somebody always moves from a room to a room with at least as many people. Someone moves from their room to a room with at least as many people. So I'm not saying who moves. So there's some freedom in that. And I've got to be careful because imagine there's only 2 rooms and both rooms have 10 people. I can't say you move to the room that has more people because there is no room with more people. So in that case, I would have to just, someone in one of the rooms would have to say, all right, I'll move. All right, everybody understand the problem? Yes?
When you say someone, are you saying that at one time only one person?
Correct. So one person moves, time 1, somebody moves. And then time 2, someone moves. And then time 3, someone moves. So what do you think the conjecture should be? Yeah, that seems a reasonable conjecture. All end in one room. And we could do some small cases and try to get a sense of what's going on. What do you think the monovariant should be?
The number of people in the largest.
Okay, so that's definitely a natural candidate.
Or the smallest.
Well, the problem is we could have many rooms of 0, because once a room is at 0, it's never going to have anybody.
Right. But it'll always be decreasing or.
Okay, so the hardest part about the monovariants is figuring out what you want to be your monovariant. So the first one you had was number of people in largest room. And by largest room, we'll just mean the room that has the most people. Okay, what else were you suggesting?
The number of people in the smallest room.
Okay. Other suggestions? And I wrote down a few myself.
Maybe like some squares of people in each room.
Have you seen this one before?
No.
Okay, email me. That's a great way to look at it.
Because then you could something that increases.
So make sure you email me. This is the best monovariant for this problem. So if you have x1, x2, xr as the people, and the sum of squares would be, say, x1 squared plus xr squared. Let's say we now move it, so somebody moves from room 2 to room 1. So we now have x1 plus 1, x2 minus 1, xr. And so this would become x1 plus 1 squared plus x2 minus 1 squared plus xr squared. And now we can look at the change. And so it's going to be this minus this. So x3 through xr squared, they all cancel. x1 squared cancels with the x1 squared. We'll have 2x1 plus 1. So we get 2x1 plus 1. And then we have to subtract off over here. We'll have, I guess we're adding, we'll have negative 2x2 plus 1. But what do we know about x1 and x2? x1 is greater than or equal to x2, and so this is at least 2. So what happens is in one moment of time, the sum of the squares increases. So how does this solve the problem?
The greatest sum is when all of them are in 1.
The greatest sum is when what?
You can prove that, the sum of x1, x2 equals r squared. That sum squared is going to be greater than any other way you split them.
Okay, what do you say is the greatest for that sum?
Basically, if the monovariant is the sum of the squares, that's always rising until
Right.
you're done. And the largest sum of squares occurs when all of the people are in one room.
So how do you know the largest sum of squares is when all the people are in one room?
Well, we know the sum of x1 through xr is fixed, right?
We know, okay.
Do some calculus.
Yeah.
Oh, we could do some calculus. Okay.
Yeah.
All right. So this doesn't seem to want to
It's
swivel. So.
fairly
All right, so we could try to do some calculus. Right? So, our constraint function g of x 1 through xn would be x1 plus xn minus n. F of x1 through xn would be x1 squared plus xr squared. And then we would want gradient of f to be lambda gradient of g. So the gradient of f is going to be 2x1 xr. Is that right? And so this should be a lambda. So this tells us that all xi are equal. Oh dear.
That's the minimum.
That's the minimum.
And I guess you can't maximize under the constraint, right?
Right. Well, we also have secondary constraints. All the x's have to be non-negative.
Yeah.
So in terms of trying to find a maximum, there won't be with this because I can just keep letting x1 get really, really large, x2 get really, really large and negative. That'll cancel each other out, and this will get larger and larger and larger. So if I try to prove this by Lagrange, I'm in trouble. So the question is, how would you prove that the largest sum is when they're all the same?
You could just take the n squared, or the total sum.
Okay.
Is x1 plus all that squared, then subtract an arbitrary, I guess partition you could call it.
Okay.
Them into the squares, and then you just show that that's a strictly positive quantity.
Okay, so I think that would be a little bit involved to show.
Well, I mean, because you could group the terms as squares, and you get plus 2.
Right. I think there's an easy way is to just go back to what we have here. Imagine we don't have everybody in the same room. What will happen? There'll always be movement. Right? So if everybody's not in the same room, there's got to be movement. And they can't move to a room with fewer people. They've got to move to a room with at least as many people, if not more. So in fact, as we go through this, what can you say about the number of people in the largest room? That never goes down. So you could also look at the number of rooms with 0 people. That never goes up. And in fact, what's got to happen is people have to be moving from rooms with fewer people to rooms with more people. So if I had a configuration where everybody wasn't in the same room, that can't maximize the sum of the squares. Because we've just shown if you have a configuration where everybody's not in the same room, movement increases the sum of squares.
Okay. So you just say that after a certain number of times, 2 times that number of times is going to be greater than Rx squared.
Yeah, basically, if you just wait long enough, everybody has to move to the same room.
But isn't that just assuming that the conjecture is correct?
No, because what you could do is you can say there's movement. And imagine the process stops and everybody's not in the same room. If it stops and everybody's not in the same room, you have 2 peopled rooms. And if there are 2 peopled rooms, someone can move from a room with either the same or fewer people to a room with the same or more people. And that will increase the sum of squares. And so when you do this, the most populous room is never going to go down.
Yeah.
So the question is, how rigorously do we want to write all of this up?
I think what you could do is you could say, let x1, the sum of x1 through xr be like s.
Okay.
Sum.
Well,
And then-
we're having it as n for n people, but
Okay, right. So n.
right.
You can show that after, Rn squared divided by 2 times,
Okay.
the sum of squares is going to be at least Rn squared. It's going to be at least Rn squared because it started out with at some positive quantity and now increased by
Well, are you saying r squared times n squared or r times n times n?
r times n times n.
I don't know if we will know that it'll be that large because if everybody's in one room,
Well, I
we
mean,
only get n squared.
I'm kind of overkilling it right now.
Oh, you're saying that this is the most it could be?
Yeah, I'm just
Yes, yes.
putting in an example
Correct.
amount,
Yes,
and then
yes. We know that the sum can never be larger than r times n squared.
Right.
And we know it always increases by 2.
So after r n squared
Steps, yes.
times, then it must have stopped.
It must have stopped.
And after it stops,
Good.
if you've done the largest room, then you can show that,
Good.
there are only people in one room, and it has to be the largest room because the largest room never went down. So it must have,
Good. So we can't exceed Rn squared for sum of squares. So therefore, at most, Rn squared steps.
yeah. Or you could divide it by 2 if
Yeah. And then we know at most Rn squared steps, the number in most populous room never goes down. And then if terminate with 2 peopled rooms, I hope that's a word, contradicts maximality. We could have kept moving. It contradicts having no more moves. Because if we have 2 peopled rooms, we could go again. And so the assumption that there are 2 peopled rooms must be false. So this is a really good problem. The interesting thing is trying to find out what do you want to do for the monovariant. And the sum of the squares of the people is a great monovariant to look at.
Could we look at this backwards to prove that the sum of the squares of,
Well, so now we know as a result that if we want to maximize x1 squared plus dot 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 plus xn squared, where the x's are summed to n and they're non-negative integers, the maximum is at n. So we can actually now deduce that as a theorem.
it's a fun way to prove it.
It is a fun way to prove it. And a lot of combinatorics. And I think this is somewhat similar to combinatorics. It comes down to trying to look at something two different ways. There's the way you can compute, and there's the way that you want. And if you can show that they're equal, then you do the computation, and then what you want is now equal to that. So we actually now get that the sum of the squares is largest when all are in one room. What if we don't require them to be integers? Let's prove this as a theorem now.
Could we just say we take some quantity that's not necessarily...
Well, yeah, so if we could then go back over here.
Just do like lambda or epsilon or whatever fun letter you want.
Oh, fun letter. Do you know what that is? The complex conjugate of c divided by c. This is typically used as the worst possible thing to see in a math paper in terms of just the formatting of it. It is absolutely horrible.
Maybe not that fun.
The other one I like to use, do you know how to say that one out loud? Z naught naught naught. It's
So I suppose if we take some quantity,
let's take a little delta.
right?
And then we have a delta squared.
So that would be 2 delta squared. I guess my concern is now, what if we set delta as always decreasing by a factor of 1/2 every single time?
So the question is, can we actually extract the theorem from this? Well, what we've just shown is the following. So, conjecture. x1, xr are in R plus. So this is, well, we'll say greater than or equal to 0. And their sum equals n. Although really at this point, what should we say their sum equals? I'm sorry?
Or you can say 1.
Yeah, we could say 1. Right, because if it equals n, we just divide everything by n. So I mean, we can leave it as the general case where their sum is n, but really at this point, we might as well say, now that we're working with reals, that their sum equals 1. That might actually make things a little bit easier for us if we look at it as equaling 1. The maximum of x1 squared plus xn squared is x1 equals 1, I'm sorry. And of course, all the other tweaks. This actually isn't that bad to show. We can show this directly. So here's the direct proof. Assume x1, x2 are greater than 0. If we look at x1 squared plus x2 squared plus x3 squared plus xr squared, since these are greater than 0, if I replace x1 squared with x1, what happens?
Can you say that again?
Sure. If I replace x1 squared with x1, what does that do to this quantity? Increases. So this will be strictly less than x1 plus x2. And the reason is I need to know that x1 is not 1. So because if it was 1, it would be unchanged. But because they're positive, and I have two things that are positive, neither one can be 1. So if I replace x1 squared with x1, I've made it larger. And then I can, of course, replace all these. And if these are 0, it doesn't change. But it's fine. I've already got the strict degree. And now, this is just equal to 1. So that's enough to prove directly that this can't be the maximum. Any questions on this? So this is the direct proof. Because if it equals n, just divide everything by n. And now instead of looking at the sum of the squares, you'll do the sum of the squares divided by n squared. Well, that's fine. If I'm trying to maximize that sum, I just maximize the numerator. So without loss of generality, and you can see now how useful it is to do this dimensional analysis and say, well, look, let's just make them all equal 1. Because everything is occurring in a really nice way. Okay, so we're comfortable on the direct proof. All right, let's try to do the proof along the lines of what we were doing there. So we want to show, okay, so now proof. I think we can probably just argue exactly as before. Assume there exists x1, x2, such that 0 less than x1, x2 less than 1. So we would have x1, x2, x3, xr, and this goes to x1 squared plus x2 squared plus x3 squared plus xr squared. And now I claim that there must be some delta we can add. Any thoughts as to what we could take for delta? And so this would give us x1 plus delta squared plus x2 plus delta squared plus x3 squared plus xr squared. Oh, yes. Thank you. Maybe I can do this carefully. Any thoughts on what we could take delta to be? Not any real greater than 0. We need it to be greater than 0, but we also need an upper bound on delta. We could take delta to be anything between 0 and x2, right? So 0 less than delta less than x2. In fact, less than or equal to x2. And then we look at the change is, well, it's 2 delta x1 minus x2 plus 2 delta squared. We chose x1 to be greater than x2, and so this will be greater than 0. So this shows that if we are in a situation where they're not all equal, we can get something larger.
So there's always an improvement.
So there's always an improvement unless
x equals 0, in which case there isn't a delta that exists.
right. So have we proven the claim now? How many of you have taken real analysis?
You could just do a proof by contradiction. Say anything not than 1, then there's an improvement.
You're making an assumption. You're making a small assumption right now. Who's taken real analysis and knows the problem that we need to fix? So one of my colleagues, so we're teaching this class online right now. One of my colleagues at Pomona College is going to be teaching graduate real analysis next year. I don't remember if it's going to be in the fall or the spring. He's an outstanding professor, one of my favorite colleagues. And so if you're interested in something like that, please let me know and I can provide more information. There's a subtle point here.
I mean,
It's
if delta's always decreasing.
well, no. I mean, you've just shown that if they're not all equal, I can get something larger by just shifting a little bit. So let's define f of x to be 1 over x, 1 minus x, 0 less than x, less than 1. Find the maximum of f of x. So where's the maximum of this function? Well, if I plot this function, here's 0, here's 1. Here it should look something roughly like this, going off to infinity. Right? This function has no maximum. What we need to do is we need to show that there's a maximum here. And this is where we need a result from real analysis. If you have a continuous function on a closed bounded set, then it has a maximum. And our function is a continuous function on a closed bounded set. It's like the hyperplanes xi greater than or equal to 0 and x1 plus x2 plus dot 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 plus xr equals either 1 or n. That gives us a bounded region, because none of the xi's can be larger than n. Our function is continuous, it's the sum of the squares. So a maximum must exist. So now that a maximum exists, assume the maximum does not have the form 1, 0, 0, 0, 0, 0, 0, 0, 0. Then we can get something larger. So this is the annoying thing. What we've done is we've shown that if there is a maximum, then the maximum is what we think. But we haven't shown that there must be a maximum. And that's where we need this result from real analysis. Okay. Any other questions on this? So we've got a few minutes left. There were 2 more monovariant problems I was thinking of doing. I will state one and let you think about it for homework and then have this conversation on Friday. And then if there are specific project Euler problems you wanted to discuss, let me know and we can go over the coding for those. There will be a coding problem on the exam. All right, so here's a nice one. So I just want to phrase it the right way. All right, so we have n numbers, 1, 2, 3, dot n, put in some order. Say x1, x2, xn. If x1 does not equal 1, flip or reverse the order of the first x1. And then repeat. So for example, let's say I start with 3, 4, 2, 1, 5. My first number is not 1, so I flip the order of the first 3. So it was 3, 4, 2, now it becomes 2, 4, 3. So it's 2, 4, 3, 1, 5. Now what do I do? So now it's 4, 2. Now what do we do? 1, 3, 2, 4, 5. And the first number is a 1. What would you conjecture? So think about that for Friday. Will you always end up with a 1? Does the 1 always have to go first? And if so, how would you prove that?
Sorry, could you just explain the mechanics?
Sure, sure. So I have some list of n numbers. So here n equals 5.
Yeah.
So 3, 4, 2, 1, 5. If the first number is 1, celebrate and you're done. If the first number is not 1, look at that many items.
Oh.
So here's 3. So I look at the first 3 items and then just flip the order. So instead of 3, 4, 2, now it's 2, 4, 3. And now since the first number is 2, instead of 2, 4, I would now have 4, 2. Now I look at the first 4, and now it's 1, 3, 2, 4. So the conjecture is you terminate with a 1 as first. Do you know any information about what the other items could be? Do you think we could have a stronger conjecture?
The conjecture and the maximum number of times.
So you could conjecture on the maximum number of times, but I'm wondering, can you conjecture on the order? So the conjecture is that if you run this long enough, you'll end up with a 1 as the first.
You can't conjecture on the order of anything past 1.
Right.
You can start with 1 and then anything
Right.
else.
I could start with 1 and anything else. Right? So if I start with 1, I can put anything I want for the next 4 numbers in whatever order I want. So there is no way I should be able to do a stronger conjecture than this. On the midterm, you are asked to conjecture the functional form of an answer to a problem. And then you're asked to prove your conjecture, or if necessary, refine your conjecture. Proving your conjecture is worth 0 points. So I'm not going to, if you're not able to prove your conjecture, that's fine. But I want you to get a sense of what do you think the conjecture should be for the problem. And so here, it's really important when you're looking at something to think, what should I be able to conjecture? And if I start with a 1 as the first place, anything can happen after that. I have no right to expect anything better than just it ends with a 1. The real danger is, could we somehow end up in a strange loop? And so the question is, what's the best way to attack this? As a hint, what do you think might be useful? A monovariant might be useful given that this is in the monovariant lecture. So, all right, we've got, let's see how much time do we have left. All right, we have about 1 minute left, so it's not really worth doing the tournament problem. I'll save that for Friday. So we've done, I think, 20 Project Euler problems. Is that enough for you to get a award from Project Euler? You have to do 25 to get the first award? You get it at 15? Okay, so everybody at least has some award at this point. Excellent, excellent. So, so look at the first 20 problems, and if there are problems that you particularly enjoyed and want to present, let me know, and you can try to coordinate, because I really want to talk about how we do the coding. And if you are going to present it, if you want to project the code, you can either send it to me and I can have it all set up on my computer, or if you want, you can bring your laptop and we can try to just interface directly. I was actually at a conference on Monday, and all of a sudden the computer stopped projecting someone's PDF. Fortunately, this person was one of the few people to actually have their talk on a flash drive. And so I had my computer over and said, toss me your flash drive. So she tosses me the flash drive, I catch it, quickly put it in my computer, it works on my computer, and we quickly connect to my computer. There was no wireless at the conference. Many of us were quite upset. We had to pay attention to talks. I'm sorry. But because there was no wireless, it meant that I have my talk on my email account. Well, I couldn't access my email account. If you are giving a presentation, you always want to have it on a flash drive on you. Most of the time you'll be able to access the web, but for those few weird times when you can't, it's extremely useful. Okay.